So now that you know how to find the experimental and theoretical probability of one event, let's build on top of that idea and worry about and learn how to calculate the probability of independent versus dependent events. So when you have compound events or more than one thing occurring. I want you to do the warm-up, try the warm-up with answering the question, what is the difference between independent and dependent events? Write down what you think is the answer there. Pause the video, complete those two, and then press play to go over them. Go ahead and pause now. So with this warm-up, you're finding the probability that a point chosen at random would fall in the yellow region. So we want the probability of yellow. Well, when you look at the yellow region, you have to make sure that you don't count the red region in the part as the yellow. So the yellow square would be an area of 9, 3 times 3, but you have to subtract out the red, 1 times 1, over the total area. So it's a 6 by 6 square, so it's 36. So the probability of yellow would be 8 out of 36. And then reduce your fraction down. So you can divide them both by 2, or by 4 actually, and get 2/9. This is about 22%. So when you're looking at a picture, like a geometric figure, you can find the probability by calculating the areas. So what is independent versus dependent? What does that mean? Well, you should know what those two words mean. You just may not have applied them to probability yet. Independent means that one event does not affect the probability of the other event, whereas dependent means one does affect the probability of the event. Typically, this is seen in the fact that the sample space changes, so the total number of outcomes differs from what it would be in the first event. Any type of problem really dealing with like cards or skittles or dice, maybe you're doing more than one roll or more than one pick, is a compound event. But depending on the wording, it could be independent or dependent. If I said you're going to, from a standard deck of cards, what is the probability of picking the king of spades and then the 10 of hearts and holding on to those cards? Well, the probability of the king of spades would be 4 kings out of 52 cards for the first one. But then after that, if you're holding on to that king, if you want to know the probability, the king of spades actually would be 1, right? But after that, if you want to know the probability of getting the 10 of hearts, there's only one 10 of hearts, but now there's only 51 cards in the deck, right? So the sample space changed, the denominator changed. That would be a dependent event. Whereas I could say, what's the probability of picking the king of spades, returning that card, and then picking the 10 of hearts? You'd have a 1 out of 52 chance of getting the king of spades. You return it, so you'd have a 1 out of 52 chance of getting the 10 of hearts. And then we would multiply those two, and we'll talk about that. Skittles, I could say, what's the probability of choosing 2 green Skittles out of the bag at the same time? Well, as soon as you place your hand on this first one, and you go and place your hand on the second one, there's less Skittles that can be in the second spot after you've touched the first one, right? So if it doesn't say replacement, if it does not say it's replaced, those will be dependent events. Rolling a die, I could roll this die. What's the probability of getting a 4 and a 3 on 2 die? Well, does this first throw affect the second throw? No. Even if it's the same die, it still doesn't affect it, so those would be independent events. Here's one more fun example of independent-dependent. You guys might know this game, Deal or No Deal. So in the game, you choose one case to be yours. I'm going to just choose 26 to be mine. And then in the first round, you have to open 6 briefcases. Well, you don't want to open the $1 million here. So out of the cases that are left, what is the probability that you will not get $1 million? Well, you have only one of these would be $1 million, right? There's only one of those. So you would have a 24 out of 25 chance of not getting the million. There's 25 cases left, 24 of them are not $1 million. If I open case 25 on my first one, and I don't get $1 million, on my next pick, what is the probability that I do not get the $1 million again? Well, now there's not 25 cases left, right? There's only 24. So the probability of not getting $1 million would be 23 out of 24. If I open another one, now there's only 23 cases. 22 out of the 23 would not be $1 million. I hope you get my point here. This would be a dependent situation because as I open the cases, there are less left for the denominator of the second fraction. So before we get into the practice problems, I want you to write two things down. We've done events like this, the probability of A or B. What's the probability of getting a 1 or a 2 on a die? With the probability of an OR situation, you find the probability of each one and you add them. The probability of getting a 1 or a 2 on a die, the probability of getting a 1 would be 1/6, a 2 would be 1/6, you add them together. The probability of getting a 1 or a 2 would be 2/6 or 1/3. We're going to do these new ones then today. What's the probability of getting A and B? Think about this. If I want just either one or the other, I'm going to have a greater probability. There's more chance of that happening. If I want both things to occur, then there's going to be less chance of that happening. So that would be the probability of A times the probability of B. You would multiply to get a smaller answer. Typically, we think of multiplication getting us a larger answer, but remember, you're multiplying fractions here, so that would give you a smaller answer. So A and in probability is multiply, or in probability is adding. For these examples, we're going to decide whether the events are independent or dependent and find the probability. You select the ace of hearts from a standard deck and hold it, and then a friend selects a king from the same deck. Independent or dependent? Well, since you are holding the first card, there will be less cards left for the second pick, so that is a dependent event. Now let's find the probability. Set up your probability notation first. What is the probability of getting an ace of hearts and then your friend getting a king from the same deck? So I'm going to say the king after, because that's going to kind of signify that we are not replacing it. We are holding on to that first card. So how many ways can you get an ace of hearts? Well, there's only one ace of hearts in a deck, and there's 52 cards. And means to multiply. And how many ways can you get a king after? Well, there are 4 kings in a deck, but now there's only 51 cards because I held the first one. You can multiply straight across, but before you do that multiplication, I prefer to reduce down as much as possible. The 4 and the 52 can reduce. So 4 can be reduced to 1 and the 52 can be reduced to 13. Now multiply your fractions straight across. You will need a calculator for this. Go ahead and type in the multiplication. Also, you can round to the percent as well. So 13 times 51, did you get 663? And then when you divide that to get the decimal and then you move the decimal over, this percent is 0.15%. That's less than 1% chance of this happening. So don't bet on that. All right, let's try number 2. You toss a fair 6-sided die and it lands on an even number. You then toss the same die and it lands on the same number as it did in the first time. Are these independent or dependent? Think about it. Does the sample space change after the first toss? No. If you're tossing a die and then you're tossing the die again, there's still 6 options. It's a new toss. Really, the first does not affect the second. So these would be independent events. Sometimes we think that they are dependent because it says you have to get the same number. But no matter what number you get on the first toss, your probability for the second toss is going to be the same no matter what, right? What's the probability of getting any one number on a die? 1/6. So it doesn't matter what you get on the first toss, okay? The probability did not change. So these are independent. We want to know what's the probability of getting even, and then you toss it and you get the same number, the probability of getting the same number. So the probability of even, how many numbers are even on a die? 2, 4, or 6. So 3 out of 6, or 1/2. And is multiply. And then the same number. So if you get a 2, what's the probability of getting a 2 again? 1/6. If you get a 4, then 1/6 is your probability for getting a 4 again. And if you get a 6, then your probability is 1/6 for getting that 6 again. So no matter what number you get first, this probability did not change. That's why it's independent. Multiply straight across. You can also get your percent. 1/12 is about 8.3%, and I'm putting the about symbols there. So and is multiply, independent or dependent, make sure you know the difference. Let's try another one. A bag of candy has 10 red candies, 12 blue candies, and 8 yellow candies. What is the probability of you choosing 2 blue candies in a row? Independent or dependent? Well, if I'm choosing them in a row, does it say I'm replacing them? No, so this would be dependent. That means the sample space for the second pick will be different from the first pick. So I want to know, what is the probability of getting blue and blue again or blue after? So how many are blue? What's the probability of getting blue? Well, I have 12 candies out of 30. And then getting a blue again. Well, if I assume that you got a blue here, how many blues are left to be picked? Only 11. And how many are left in the bag of candies? 29. Perfect. Before you multiply, I like to simplify. So 12 and 30 can be simplified down. I would keep your work neat though. You can take out a 6 and you'd have 2 over 5 instead. That's a little nicer. 2 times 11 is 22. 5 times 29 is 145. And this is what percent? Go ahead and type it in on your calculator. 15.2%. 15.2%. Nice. Okay, let's try number 4. A quarter is flipped 3 times. What is the probability that the coin lands heads up at least once? Anytime you have a word like at least or at most, be careful with that. That's kind of tricky. So we want to know, what's the probability of getting a heads at least? What inequality symbol would be equivalent to at least? So I want to know the heads. If it's at least, it's going to be more than, right? Or equal to 1 time. So I want to know, what's the probability of getting a heads more than or equal to 1 time? This is an event in which it would help to list out the possibilities or think about the complement. Let's list out, if you flip a coin 3 times, what could happen. You get heads, heads, heads. What else could happen? Heads, heads, tails. And then maybe you could get heads, tails, heads. Or you get tails, heads, heads. Okay, those are some options. Give me some more. These are all the options with all heads. These are all the options with 2 heads. What if I get 2 tails? And what if I get all tails? So from listing these outcomes, what is the probability of the coin landing heads up at least once? How many of these land heads up at least once? 7 out of the 8 possible outcomes. Now this is a great event that you could also think about the complement. The complement of heads landing at least 1 time would be heads landing less than or equal to 1 time, which is also the same thing as no heads, right? So if you look at your outcomes, how many ways can you get no heads? Only 1 way. So the complement, then, you would just subtract from 1 to get your probability. I think it's easier to list out the outcomes, but this is a great example of how you could think about the complement and subtract it from 1 to find your probability. Perfect. Okay, so here's the deal. We have a couple more. I want us to do 5 and 7, but I want you to try 5 and 7 first, then press the next video to go over it. 5 and 7, okay, so circle those. Then here's the deal. 6 and 8 are an optional challenge, okay? So they will be in the next video, but they are optional. If you have extra time, you can choose to do them, but you do not have to do them. Go ahead on to the next video.